13.3, the fundamental theorem of line integrals, video 2. Before we move on to answering the question, how can we tell if the integrand of a line integral is the gradient of another function? In other words, if the integrand is conservative. Let's take a look at a real quick example. Suppose we have a curve defined by the function, vector function r of t equals t squared plus 1 as the I component function plus sine of t as the j component function on the closed interval 0 to pi over 2. If our function f of xy is equal to x squared plus y squared, evaluate the line integral over the curve C of the gradient of f dot dr. This is actually pretty straightforward to begin. It's going to get a little messy at the end, but messy arithmetic is just arithmetic. So according to the fundamental theorem of line integrals, which I think I'll abbreviate FTOLI, F-T-O-L-I, lowercase o for the word of, according to the fundamental theorem of line integrals, we know that the integral over the curve of the gradient dot dr is going to be f of r evaluated at the end point of the interval, the right end point, pi over 2, minus the function evaluated at r of the initial value in the interval, so 0. So we just have to work this out. So let's see what r of pi over 2 is equal to. We would put pi over 2 for all the t's, so this would be pi squared over 4 plus 1 as the I component function. And we could write it as the I component, and we could write it that way, or we could just put comma, with the understanding that when we take the, when we insert a vector in here, what we're really inserting are the vector's components. And we have to continue by inserting the pi over 2 into the j component function. So we get sine of pi over 2, which is 0. So that's comfortable. This is going to get kind of ugly, but it's just arithmetic. And what do we get when we substitute 0 into the vector function r? Well, for the I component, we get 0 squared plus 1, which is just 1. And I need to back up for a second. I know some of you are screaming, sine of pi over 2 is not 0. You're correct, sine of pi over 2 is 1. When I created this problem, I was going back and forth on whether to put sine or cosine here, so my apologies. But I digress. To evaluate r at 0, we substitute 0 for t here. 0 squared plus 1 is 1. That's the I component, so that's the first input of f. And when we substitute 0 into sine of 0 is 0. So that part will be pretty easy. Excuse me. Got to forgive me. It's allergy season. All right, so now let's stick all these things into our f function. Our f function simply says add, take the sum of the squares of the inputs. So we would have to, oh, this is going to get fun. Take pi squared over 4 plus 1 and square that, plus 1 squared, minus 1 squared plus 0 squared. Well, the 1 squareds cancel. Excuse me. Oh, curse you, allergy season. Sorry, I know that's lovely, but life goes on. Plus, you've all had snotty noses and had to blow them before. All right, so the 1 squareds cancel, the 0 squared doesn't matter, so really we can just say it's pi squared over 4 plus 1 squared. So the arithmetic really wasn't as bad as I thought, unless you really want to write this out and FOIL it. If you really wanted to do that, just because it looks unfinished, you would have pi to the 4th over 16 plus pi squared over 2 plus 1, if you FOIL it out. My point is, when you're evaluating the line integral of a gradient, all you have to do is evaluate the original function at the endpoints of the curve defined by r, which is defined over this interval. So it's pretty straightforward. Hooray!